Simulation of Basic Analog and Digital Circuits with TINACloud. In this video, we will quickly go through the simulation of basic analog and digital circuits using TINACloud. Here we will show just the main steps of creating and simulating these circuits, but for each circuit in this video we have a detailed tutorial video as well. Creation and simulation of an RLC circuit.
We will create the RLC circuit shown on the screen. First, select and place the resistor from the basic toolbar.
Then add and set the other components.
Next, connect the components with wire. We still need to add the ground and a voltage pin from the meters toolbar. Let's check the voltage in the voltage generator. The default setting is a unit step, and its voltage is 1 volt. It will jump from 0 to 1 at the beginning of the simulation. T equals 0. Now we still need to change the default values of some of the components. Let's change R1 to 200 ohms and C1 from 1 microfarad to 1 nanofarad. Now the circuit is ready for analysis. Let's first make a transient analysis. Select Transient from the Analysis menu. Set the end display time to 50 microseconds. Next, change the start condition to 0 initial values. Then press the Run button. Okay, now let's add the diagram to the schematic editor window to store it together with the circuit schematic. Select the Insert button denoted by a green plus sign, then click Insert Diagram. Now let's generate the accurate closed formula describing the transient response using the symbolic analysis capability of TINACloud. From the Analysis menu, select Symbolic Analysis and then Semi-Symbolic Transient. The symbolic result appears. We can also draw a diagram using the formula and compare it with the numerical result. They are very close to each other. The difference is due to the numerical solution used at the transient analysis. Okay, now let's add this formula to the schematics editor window. Note that you can also customize the formula. Okay, let's continue with the AC analysis. Go to the Analysis menu, select AC Analysis, then AC Transfer Characteristic. In the AC Transfer Analysis dialog, set the number of points to 500 to have a finer diagram and press the Run button. The AC Amplitude characteristic appears, but at the same time the program has calculated the phase, Nyquist, group delay, and AC Bode diagrams. Next, add the AC Bode diagram to the schematic editor window. Pan the schematic editor screen. Go to the Insert menu and select the Insert diagram. Finally, let's generate the closed formula of the AC transfer function using symbolic analysis. From the Analysis menu, select Symbolic Analysis, then Symbolic AC Transfer. We can also add it to the schematic editor window. Press the green Insert button on the toolbar,
and then select Insert Symbolic Result on the menu.
Finally, add a title and rearrange the screen to get your preferred layout. This concludes our demonstration on creating and simulating an RLC circuit.
Creating a fourth-order active filter circuit. This circuit consists of a voltage generator, 2 resistors, 2 capacitors, and an operational amplifier, OPA364. We will create the circuit shown on the screen. First, place the voltage generator, 2 resistors, and 2 capacitors as shown next. Set the component values as follows. Next, add the operational amplifier to the circuit. Click the Spice Macros tab, then click the operational amplifiers icon on the toolbar. Add a few more components to the circuit. Select two grounds from the basic toolbar and a battery. Now, the first block is ready. Create the second block using the multiple selection, copy and paste. Finally, add two outputs to the circuit using the voltage pin components from the meter's toolbar. Now, the circuit is ready for testing. Select Analysis, AC Transfer Characteristic. Set the frequency range, then press Run. Several diagrams will be generated, included amplitude, phase, Nyquist, group delay and Bode diagrams. You can run two cursors on the diagrams and read the values and the difference. You can also insert diagram and store it together with the circuit schematic. Select Insert Diagram from the Insert menu, then the AC Bode one from the list. Use the Zoom Out command so that all objects will be visible. Add labels to the curves using the Text tool. Finally, add the title to the circuit.
Simulation of a half adder with 4 basic gates using TINACloud. We will create and test a half adder circuit in TINACloud. We will use basic OR and NOT inverter gates, high-low switches, and voltage pins for the outputs. Click and place the components, and then connect them. Okay, let's rename VF1, VF2, and the switches. And the circuit is now complete. Now, to test the circuit, click the Dig Interactive button. Play with the switches toggling between low and high levels to produce all the input combinations. If both inputs are low, sum and carry are also low. If just one input is high, then sum is high too and carry is low. If both inputs are high, then sum is low and carry is high. Now modify the inputs to plot a time diagram and replace the switches with pulse sources. To produce all the needed input combinations, for a time period of 1 second, set the PS1 pulse source to high from 0.2 seconds to 0.6 seconds. Next, set pulse source PS2 from 0.4 seconds to 0.8 seconds to high. Add more voltage pins to the inputs of the circuit to see the input signals on the diagram. Rename VF1, VF2, also rename sum to sum:3. These settings will separate the signals and determine their orders in the diagram. A will be at the top, followed by B, sum, and carry. Finally, run digital timing analysis from the Analysis menu. Click the Analysis menu and select Digital Timing Analysis. Set the simulation end time to 1, then click the Run button in the Analysis display window. Now all signals are displayed separately in a time diagram.
Arduino blinking LED simulation using TINACloud.
We will create and simulate the Arduino-controlled blinking LED circuit on the screen with TINACloud. Click the Insert button, denoted by a green plus sign, to invoke the Insert menu, then select Insert Global Macro. Select Arduino Uno from the Global Macros dialog window, then press OK. Next, select and place the voltage source and the ground from the basic toolbar and connect them to the Arduino Uno board as shown in the video.
Now,
create the output part of the circuit. Select and place the LED from the optoelectronic toolbar, then select and place the resistor and the ground. Finally, select and place the voltage pin and connect the components with wire to the Arduino board. Now load and compile the Arduino code. Click the Add button in the MCU IDE window, then select the previously downloaded C code in the blink.ini file,
or create and save a file with the simple content shown on the next screen.
Okay, let's quickly follow the operation of the C code. Initialize the digital pin LED_built-in as an output. Call the loop function to create an infinite loop for the instructions between the opening and closing braces. Turn the LED on with a logic high voltage. Create a 500 millisecond delay. Turn the LED off with a logic low voltage. Create a 500 millisecond delay. Return to the opening brace of the loop function.
Now, compile the code and save the changes.
To see the generated waveform, run transient analysis from the analysis menu. Change the end display value into 2 seconds, then press the Run button. After the simulation ends, the diagram window appears. It shows a symmetric square wave with a period of 1 second. Okay, now let's change the waveform to an asymmetric square wave with the half periods of 1000 milliseconds high and 500 milliseconds low. In the MCU IDE window, change the Turn the LED on delay value to 1000.
Compile the code and save the changes.
Run again Analysis Transient. The required waveform appears. Okay, now let's check the operation using the live interactive mode of the program. Change the simulation time unit to 1 second and press the OK button. Press the TR button. The LED starts blinking with the required timing. Release the TR button to stop the blinking. Finally, let's see how this circuit works in real life. This concludes our Arduino blinking circuit simulation video.